Good morning, good afternoon, and good evening, everyone. My name is Aniruddha Jasu. I'm the Technical Marketing Engineer from HPE Aruba Networking team. Today, we would be talking about an update on Redistribute connected hosts on Border VTEP. Following would be the agenda. We would be covering overview of the description we just discussed, talk about certain use cases, details, configuration, best practices. We'll get into certain troubleshooting and end the session with a demo.
All right. With respect to overview, right, please do make a note that we would be covering a particular type of topology which would be used, and I would be talking about the connectivity, the placement, the host names, so that it will be easier for everyone to recollect that for the entire slide. So it's all the same. So please do concentrate on what I'm about to say with respect to topology, and then we'll get into the overview. The topology which you see right here is a compressed way of the upcoming topologies, wherein I'm trying to highlight the overview of the feature. Yeah, as you see on the pointer, this is the Fabric 1, Site 1 or DC1. On the right side, you will find Fabric 2 or DC2. They both are connected via interfabric EVP and VXLAN tunnel. It would be an eBGP tunnel, right? And the highlighted devices are the border leaves, border VTEP of each site. So this B1A and B1B, they are in BSX. So these are the border leaf for Fabric 1. On the right side, you will find border leaf for Fabric 2. They are having their own host connected. Mind the subnet, which we are going to utilize for the entire session, is 20.1.1.0 network. Host 2 is .7, host 3 is .8. They are directly onto our border leaf. We are unable to switch. Now, this is an VXLAN network. It's a subnet stretch on VLAN 1001. So the L2VNI would be 1001. These hosts are on this VLAN. Okay. Now we are talking about this feature because we want to send these hosts information to the external WAN network, which is in fact a non-VXLAN network. So we are doing that either via OSPF connectivity between router 1, which is the WAN router of Fabric 1 border VTEP, or via BGP between them, either one, depending upon the requirement. And on the other side, you have WAN router 2, which would be connecting to a border VTEP of Fabric 2, right? They are all on the top. You will find these WAN routers having multiple other routers connecting to the internet or the WAN, but they are on non-VXLAN network. So this is the glimpse of the upcoming topology and this particular slide. Now, the overview of would contain a 10-12,000 update. Basically, this feature came into that particular release. Now, before this particular feature, which is without redistributing connected hosts over OSPF or BGP, what used to happen? So what are we doing? We are redistributing these hosts on border VTEP. So everything happens here. Before we were doing that, what used to happen is the border VTEPs would be sending out the host information with /24, that is by redistributing connected. So you have a very general host information, that is 20.1.1.0/24, going to their own WAN routers from border VTEP, which you see here. From the other side, you will see the same. Also, you would find that the hosts, the north-south traffic from top to bottom, from WAN to connected hosts on border VTEPs will reach border of the opposite DC, as you see, the black direction here, right? This may lead to traffic drop in case of inline firewall here, right? Ideally, you should a very basic requirement would be that you should reach your host 2, for example, via router 1 from router 3, and then directly to its own border VTEP rather than the other site border VTEP and then to the host, right? So this is what is happening today, and wherein you also have learned the other hosts from the second DC into the site 1 via EVPN, and hence the confusion and the non-VXLAN network, right? So what happens before connected host redistribution over OSPF or BGP? Traffic from router 3 towards 20.1.1.7, which is here in Fabric 1, will traverse through RTR2, then to B2, that is the border 2 of Fabric 2, and then to border 1 to reach the host, instead of directly coming back from router 3 to router 1 and B1. This is what is happening today. So with the new feature which we have, which is connected host redistribution over OSPF or BGP, we are ensuring that the redistributing connected host on border VTEPs provide optimal routes in upstream routing domain here through the presence of appropriate longest prefix match entries, which is what we want, and that is how it's supposed to be. It's directly coming back here with this feature. For example, traffic from RTR3 towards 20.1.1.7 will utilize RTR1 to border 1 path, and traffic from RTR3 towards 20.1.1.8 will utilize RTR2 to border 2 path. Yeah, this is what we are going to achieve with this feature. And you see we have highlighted the /32 here, which is in bold, saying that it is going to the RTR1 and 1.8 is going to RTR2 with /32. And the other one would be their backup. We'll talk about that. But basically RTR3 will receive its own host routes for the RTR1 WAN router for Fabric 1, RTR2 WAN router for Fabric 2. Okay. What we have today in 10.12.1000 is the feature called Redistribute Host Routes in OSPF version 2 and version 3. We also have Redistribute Host Routes in BGP IPv4, IPv6, unicast address family, right? In 10.13.5, that is this release, you also have OSPF distribute list and a route map support for this feature, right? For redistribute host routes over OSPF or BGP. So we would be utilizing all of these parameters to ensure we have a seamable solution, right? And hence the highlights here in the overview section. Let's get into the use cases. What are the use cases of this particular feature? Now, when you have what you see on the screen is similar to what you saw on the overview section. Now I've expanded that into much more larger and detailed. Let's take a few minutes to understand this, because the same topology, the same nomenclatures would be used for the entire session. So it's very crucial you understand here. Now you know about the upper cloud, which is a WAN non-VXLAN network, right? You have a number of routers. Maybe we are using WAN router 1 for Fabric 1, WAN router 2 for Fabric 2, and they are connecting to router 3 and so on. Basically, they are running OSPF or BGP, right? And this would be the border leaf for Fabric 1 connecting to the RTR1, running OSPF or BGP, similar to the other site. Same VLAN 1001 extension, L2 VNI 1001. Hosts now are expanded. You see, you saw host 2 earlier connecting to border leaf 20.1.1.7. Host 3 was 20.1.1.8 connecting to border leaf of Fabric 2. Now you would find host 1 and host 4 as well, which are on the extreme left leaves, which are not border leaves, but they are leaves on their entire fabric. So you have these 4 hosts, right? And we would be utilizing them. You will be running IPGP EVPN session between the leaves of a fabric of a DC, and they are connecting via their spines, right? Which is pretty straightforward and similar to the other side, right? and you have this VIS 20.1.1.1 across all the VTEPs, and they have intra-fabric, as you see the amber curve here, intra-fabric EVPN based VXLAN overlay tunnel, and the blue one would be the inter-fabric, right? All right. So what's the use case here? Multi-ITC and WAN routing. Now with the multiple site, right, we are actually stretching the VLAN L2 VNI connectivity, right? So multi-fabric EVP and VXLAN is the setup, is the scenario. VLAN extensions between DCs, right? That is what we're trying to achieve. Dedicated border leaf on each fabric, which you saw that here, right? OSPF or eBGP between fabric borders and WAN routers. Yes, as you see on the diagram, OSPF or iBGP between border VSX primary and VSX secondary for resiliency. One uplink failure, you have another one intact, right? This one. Okay. Mainly a data center use case, but can also apply on campus for potential local server attachment on border VTEP, right? But we will be concentrating more upon the data center use case, as you see on the screen. And where is this particular feature getting implemented is purely on border VTEP. Okay. Now, use case one would be the data path requirement. When I talk about data path, is about the host communications, right? The traffic, data traffic. Now, data path requirement one, DC1 or DC2, either way, you can consider one to make things simple. South to north traffic, that is from bottom to WAN or internet, as you see the directions here. The nominal situation would be for each host, traffic to WAN or internet should exit locally on the site, right? Let's consider this. They should exit locally through border VTEP 1, which is their own border VTEP, to their own router and to the internet, right? That's the nominal situation. Now, for the backup situation, which is the use case 2, let's say something happens here. You see the red marks, the links goes down, the WAN router goes down. You need a backup too. So in case of failure of local connectivity to WAN or internet, traffic from each host, right? Let's consider H1 and H2. Each host of one DC should be able to use interfabric, this blue color thing which you see, interfabric VXLAN tunnel as a backup path to reach WAN internet destination. It's pretty straightforward with the diagram. So this is the backup path, and that is an ideal way to reach, and that should be the case, right? So that's the backup situation. Example path from RTR1 fails, so it should go via border 2 or fabric 2 and then to RTR2. Same goes with the other way around for fabric 2 to fabric 1. Okay, use case 3, data path requirement. What else can happen in a multi-fabric situation, right? You may have inter-fabric communication. So host from one fabric wants to communicate with the host of other fabric, and they should be easily communicate with each other through the EVP and BGP, right? So fabric 1 host to fabric 1 host within the fabric, L2 or L3, overlay traffic through intra-fabric VXLAN tunnel, which is what you see here. That should happen. And fabric 1 host to fabric 2 host, which is over here, L2 or L3, overlay traffic through inter-fabric VXLAN tunnel. The communication should happen, right? That's the nominal situation today and should happen. Now, the backup situation to this is that the scenario would, like this particular scenario, should be covered by underlay routing to maintain interfabric VXLAN tunnel connectivity, even if data center interconnectivity fails, right? So either the underlay is able to route and allow VXLAN traffic between the border VTEPs, or the traffic between DC gets dropped, right? We do not want our one DC host data traffic to go to the WAN, to the internet, then go to other WAN router and come back. That's not an ideal way, right? We do not want our communication to do that between the traffic, between the fabric. So the backup situation should be the underlay should be intact, or the routing between the fabric should be intact, or the traffic gets dropped between the DC. That's the east-west traffic we're talking about. Okay, that's the use case 3. Now, with respect to use case 4, we will be talking about top-down, that is the north-south traffic from internet to the DCs, how the traffic should be. In the nominal situation, we would want for each host, traffic from WAN should enter the closest VXLAN fabric border, right? This one, to the destination host. Now, if we are talking about this path, from router 3, it should go to router 1 and then to border 1 and then to host 2 or to host 1, right? That's the normal situation. The backup situation to this would be it should go via router 2 to the other side and then go through EVPN, external EBGP, and then get into the site 1, right? That's the backup situation, and that should happen, and that should be the case. So that's the north-south situation, right? So these are the use case for the data path requirements. Let's talk about the details of it on the control plane. How are we going to achieve them, right? So for today, in 10.12,000 update, we have something called as host redistribution on border VTEPs, right? We are sending today without the host route redistribution, we are sending the entire network, right? Destination host on the right side, if you see without host route distribution, what is happening is destination host, that is H2, H3, which are directly connected to border VTEPs of a fabric, learned locally as ARP or ND, which is IPv6 entry on border VTEP. These host 2 and host 3 are not advertised locally in OSPF or BGP. Hence, no longest prefix match route entry in the local WAN router. This is what is happening today. So what is the situation? This 20.1.1.0/24, which is the SVI, is redistributed as a connected and advertised in OSPF or BGP equally from Fabric 1 and Fabric 2 borders to WAN routers, right? This border is sending .0 network. This border is sending .0 network to their own routers. So border connected host 2, host 3 routes are learned through EVPN, this one, at the opposite DC border, leaked from EVPN to IPv4, IPv6 address family, redistributed into OSPF, then advertised to WAN router connecting the remote DC, right, which is here. This leads to north-south traffic reaching the wrong DC, which is what we saw in the overview section, right? So this is what is happening today. This issue exists only for stretch subnets, mind it, as I said, and hosts connected on border VTEPs, which is H2 and H3. There are no problem for non-border connected hosts, that is H1 and H4, because we'll talk about it, but I'll tell you here that we are already having this feature redistribute host route in under EVPN context, right? Today we have that. So we are redistributing this host under EVPN and they are getting learned properly, right? So there are no issues on H1 and H4. We are talking about issues with H2 and H3. And hence, redistributing host route becomes crucial to support server attachment on border VTEP. So with host route redistribution, now comes the feature. What is happening is host ARP or ND entries, both dynamic and static, locally learned on the VTEP, border VTEP, are being redistributed and advertised as /32 or /128 routes. ARP entries into /32 or /128, make them as routes, send them into the RIB, right? And redistribute under OSPF, send that to the WAN router. So these routes are now the longest prefix match entries on the upstream routing domain at the right location. So this border border leaf will be sending /32, the exact host, into its own WAN router. So this WAN router knows where to go, right? Host route redistribution in IPv4, IPv6 address family does not redistribute host prefixes learned from other BGP peers, right? They do not do that for H1 and H4 routes are leaked from, those are coming from EVPN, right? Those are not directly connected to border VTEP. So they are not getting redistributed by this command. So only locally learned host ARP entries are redistributed with this new command. Okay. Host entries are in ARP or ND ASIC table. They are not duplicated in FIB ASIC, right? To optimize silicon space. So show IP route VRF, whichever VRF you're using. On board where you're doing distribution host route, you would not see that. I'll show you, but we are trying to optimize the silicon space here. Show IP RIP will display these newly connected host, redistributed host routes, where there is a new type of route type or new type of entry, which we call, which is assigned to these routes, called as H, as host routes. Okay. These redistributed RIP host entries are sent to peer devices, which are the peer device, their own router, WAN router, through OSPF, this one, or BGP. On peer nodes here on the router, WAN router, host prefixes appear as route entries. They are in their routing table now. So show IP route on WAN router will display these hosts 20.1.1.7 as /32 along with H1 and H4 as well, because H1 and H4 would have come through EVPN to them. Yeah. So we have a full house with the host redistribution with this new command. Okay. Now let's talk about the control plane of the use case one, which we just discussed, right? What is that? We are talking about south-north traffic, right? To the WAN, south-north traffic to the WAN. The nominal situation would be this: we are trying to ensure that we send out default route on the router one, basically on the individual local WAN routers. For the fabric one, be border one, you will have a default route being sent by the router one, which is like this, as you see on the screen. There's a default route on this particular router one, and we are doing default information originate under OSPF one. VRF1 is what we are using or considering here, and we do default information originate, sending the default route to the border VTEP. Similarly, that is being done by the other fabrics WAN router. So south-north data path, which is what we discussed. Now default route is in the OSPF sent by RTR2 to B2 or RTR1 to B1. So we are basically sending a default route. All leaf VTEPs need to know about the default route, right? All of these leaf, border leaf, the non-border leaves, everyone should know about the default route, which is being sent by its own gateway, right? It could be firewall, it could be WAN router, so that these host also knows how to reach internet, right? So to achieve that, we are going to redistribute OSPF default route into BGP, because this is how they are connecting. All the VTEPs are connecting through iBGP VPN. So we are redistributing OSPF into BGP. That means we are redistributing default route learned by OSPF into BGP. Now, through this redistribution, default route is also sent to Fabric 1 B1, right? Or Fabric 2 B2. So basically, when you are sending a default route from RTR2 to border leaf of Fabric 2, you're also sending the default route through eBGP interfabric LAN, and this particular border VTEP now has two unique default route learned today. One directly from its own router, another one from the peer interfabric border leaf, right? Now, B1 learns two default route. one from EVP and EBGP with an administrative distance 20, and one from OSPF with the local exit administrative distance 110. Now, what is the problem here? The problem is AD value. AD value is 110 through OSPF, and it's learning through EBGP, which is 20. So now border 1 would be pointing to internet gateway, default one, through EBGP VPN to other side of the DC, and then go to the other router, which is not what is the ideal situation. It should go locally to its own WAN router, right? To fix this, OSPF distance is decreased, which is lower than 20, which is EBGP AD value. In our entire setup and the demo, we would be using the distance as 12, which is locally locally to that particular VTEP, and to make sure that OSPF route locally preferred on B1, right? So that this particular border VTEP can exit through its own WAN router it has learned the default route and then go to internet. So this is the highlighted command here, which you see, and I've also highlighted the redistribute host routes command under the router OSPF context. So how are we mitigating the problem of south to north traffic? In the normal situation is via this. Okay. Under EVPN on the extreme left corners of the sites, like leaf 1 here on fabric 1 or leaf 1 here on fabric 2, you have under EVPN an already existing command redistribute host route, which is what it's helping the host 1 to redistribute as to the other border VTEPs. Right, so this has already been there. It's not a new feature. I'm just highlighting how H1 is getting learned. We're only talking about H2 and H3, right? Okay, so let's get into the requirement 2, which is the backup of the situation, right? For south-north traffic. Now, if the RTR1 goes down or the link between them goes down, the OSPF default route learned, right, on RTR1 failure, EBGP EVPN path is taken to reach, this one is taken to reach the other WAN router through border VTEP 2, border 2 here, and then go to RTR2 and then to internet. This route is also required. It's not that we don't need it, right? But that is not the optimal path. That was the backup path, and we need that backup path. But ideally, without those distance and other configuration manipulation, it was making that backup path itself as the primary path, which is not what we want. So we are controlling that. So for the backup situation, if this goes down, we have a route to reach internet through other site, to other router. Yeah. And we are using those commands. Okay. Data path requirement 3. Now, this we talked about in the use case east-west traffic, right? How east-west traffic, H1 should be communicating with H3, H4, H2 should be communicating with H3, H4, etc. And they should be communicating through this blue EBGP, EVPN connection, not through the external network, right? So for east-west data path for L2 or L3 overlay network, host to host data path between fabrics must go through interfabric VXLAN network, right? Tunnel. Now, host routes learned in the WAN routing domain. So basically, when we are redistributing OSPF into BGP here, right, which is what we did for the default route in the previous slide. So while doing that, we also have host routes learned in the WAN routing domain, because each router will also know about their own hosts. So WAN routing domain should not be relearned on borders from OSPF protocol, right? From here, it should not be relearned in the from the OSPF back inside the border VTEP. So one should choose the option to implement such filtering in the OSPF distribute list. Remember, I talked about distribute list, which will be released in 10.13, and we are utilizing that feature here so that east-west traffic is nominal, right? So once again, the host routes learned in the WAN routing domain should not be relearned on the border from OSPF protocol. These border VTEPs already know about their own host routes. They should not relearn that from the non-VXLAN networks. To avoid that, hence we are trying to deny this. We are trying to say that we use distribute list. We deny everything except permitting the default. So border VTEP will know that to reach out, I have the default, which we are permitting, but we are denying everything else. That is relearned host routes from the routers. And that is what I've highlighted here. There is a prefix list called default only, which we have created, and we are permitting the default, and then we are denying everything else, right? And then we call that prefix list in the distribute list of that particular OSPF. Now we are running OSPF here, right? This is OSPF scenario. And distribute list prefix default route in. With that, whatever is coming in, if the host routes are coming or sent by router, WAN router, border VTEP will deny them, and we will have an east-west traffic seamless. Okay. For the requirement number 4, which is the north-south traffic, top-bottom situation where from the internet we are returning back to the host, what would be the nominal situation? We talked about it, and this has been drawn here. If we look at that, traffic from WAN or internet should enter the closest VXLAN fabric border to the destination host, right? From here to reach host, it has to come via RTR1 to border VTEP1, right? The backup would have been from RTR2, which is the different situation. To achieve this, what needs to be done, right? BGP redistribution to OSPF, right, must be controlled with route metric settings so that for a given host in Fabric 1, the metric advertised from B1 to router 1 is lower than the metric advertised from B2 to router 2. Basically, we are trying to control the metric here, right? And we'll find the ways. I'll tell you how we are doing that through route maps, but we are able to control the metric, ensuring that the hosts from B1 are getting redistributed and have preference to local exit of our RTR1 so that when the return traffic from north-south, it takes this path, right? In order to match on local host route, multiple options are there, right? We can achieve this in different ways, standard communities, local preference, right? We can do many things. What we are trying to do here in this scenario is using local preference as our tool. Now to do that, BGP to OSPF, there is a route map which matches on local preference value, which is the default 100, to identify local hosts, H2 let's say, of the fabric and set that to lower OSPF metric. So inter-fabric EVP and eBGP peering reset the local fabric local preference to 90. So we change the routes which are coming from other fabric and assign them as local preference 90 and set a higher metric, which would be our backup path, right? So fabric 2, border 2, will redistribute BGP route to OSPF with metric 200 if local preference is equal to 90 and with metric 100 if local preference is 100. Yeah, how are we achieving that? You see, we are creating a route map called from other fabrics, right? And we set a local preference as 90 to them. Now, where we are using this route map under L2 EVPN BGP context, right? We say this neighbor, let's say we are using this here, border 2 of fabric 2, neighbor to it would be border 1 of fabric 1. We say neighbor border 1 fabric 1 route map from other fabrics in direction, right? We use that route map saying that whatever comes in from the other fabric, set the local preference as 90. By doing that, we create a route map called BGP to OSPF, right? And we match the local preference. If the local preference is 90, set the metric as 200, which is higher, which would not be preferred, right? Which is the backup path. And whatever is rest of the local preference, which is 100 by default, set their metric as 100. So I hope you have understood what we are trying to achieve here. For the north-south traffic, whatever routes coming in from the other fabric, set the local preference 90, make the metric as 200, and whatever is there in the local fabric, the metric is anyways 100, and local preference is also 100. So that is preferred. That is what we have tried to highlight here in this with the bold, that the bold 120.1.1.7/32 will have metric 100, and dot 8, which is the other side, will have a metric 200, which will be the backup for them. Right? Okay. Data path requirement 5, to achieve that, what needs to be done on the control plane, right? The backup situation, which I just already spoke. Let's say this goes down on the left side. So for 20.1.1.7, which was the ideal upstream was RTR1, now it has to go through the other side, border VTEP, and then to the WAN router 2, right? But it had a metric of 200, remember? So, which is fine because now it is the backup situation. Now it will use this because the uplink, direct uplink to its own router is down. So that's why we need that route also. We are not denying that. And we are marking them through metric for the backup situation. And that is what I've highlighted here with the same route maps, just highlighting which route map is getting used to achieve this. Okay. Okay, that's about the data path of the host communication, north, south, south, north, east, west, and how we are achieving them on the control plane with the commands, with the route maps, with the redistribute host routes, with the distribute list, as well as the distance manipulation. Let's get let's take a little break or to understand what more details about this particular release. 10-12,000 release. We have connected host route, this host route redistribution for OSPF version 2, version 3, BGP IPv4 address family, IPv6 address family, unicast one. We have these many platforms supported, basically 8325, 8360, 9300, and 10Ks. They all support this particular feature. From 10.13 onwards, there is a route map support for redistribute host route context, right? It's an extension to it, and that so we can control what needs to be redistributed locally as well. So hence the route map for that, and that is actually in 10.13 release onwards on the same platforms as you see. Okay, with respect to configuration, I have already given you the glimpse on where, in which context we are applying using this redistribute host route command. But just to have a context here, we are going to use this command on the border VTEPs only, and on the border leaf, you will get into the OSPF router context, and then you will type in redistribute host route. You also have redistribute host route map, which I just talked about in 10.13. And this is how it's going to look in the router OSPF context. Similarly for version 3, for BGP IPv4, IPv6 unicast address family, you will be applying same on the border VTEPs, and under address family IPv for unicast, you will redistribute host route, the same command, right? But under VRF, address family IPv for unicast. Similarly on IPv6 unicast here. Command syntax remains the same. This is okay. Now we are using the same topology as you see. We are redistributing BGP to OSPF, OSPF to BGP, and we are lowering the metric for local host and increasing the metric from other fabrics in, sending default route. So it's very important because WAN router, when we are talking about, we mostly would require defaults, and the rest of the things will be taken care by the WAN router. So default route is being sent, right? And we are also using the metric manipulation to ensure that we have backup and nominal path for each host to reach internet. On the routers, we are sending default information originate, right? They may be having their own default route. On the border VTEP, I have highlighted what we just spoke about in detail and how it looks like. So as I said in the earlier slides, we can achieve this through local preference, the metric manipulation I'm talking about, or standard communities, etc. Right? It depends upon the requirement. So what I've highlighted here is the local preference one, and what we're doing with the distributor list, denying everything but accepting the defaults, right? Okay. Now, with respect to trying to highlight what happens if we don't do what I just said. That is, when we do not use distributor list or we do not change the distance. I told you about the theoretical approach of it. Let's look at the outputs on how it looks like. Okay. So right now in this slide, you will find when distributor list is present and the distance is 12, which is lesser than eBGP AD value. It can be anything. It does not necessarily needs to be 12, lesser than 20. The solution is expected, right? That is what I'm trying to highlight. And you will see that here on the border VTEP, I'm trying to show you the routing table. And you see what I've highlighted here is the host routes, right? See my laser pointer 20.1.1.6, 7, 8, 9, right? So 6 and 8, 9, 7 is not here. Why? As I said, redistribute host route when executed on the border VTEP, you will not see them in the fib. You will not see them in the routing table. You will see them in the RIP table of the border VTEP. You will see those .7 in the routing table of the adjacent device, that is router. Hence, you're not seeing them here. It would be in the RIP table here. So in the routing table of border VTEP, what I'm trying to show is the 20.1.1.6, which is its own intra-fabric host, right? Host 1 is being learned through 2.2.2.2, which is nothing but our loopback address of leaf 1, right? This is what I'm highlighted here, leaf 1 loopback address here. It's learning through that intra-fabric, as you see. IBGP AD value is 200, and .8 and .9, which is the inter-fabric, it's the host from other fabric. So hence it is using eBGP, and it has an AD value of 20. And 11.11.11.11 is the loopback address of the other border VTEP, right? So that is what I've highlighted here. So this is how we want it. We want to learn it correctly, right? So this is expected. Now, what happens when distribute list is not applied and we remove distance value 20? Same output, right? You will see that 20.1.1.6, which is host 1, is being the next hop being the edge router, the router which is actually the WAN router here, right? So the WAN router interface, the interface which is connecting to our border VTEP, it's pointing towards that. If I don't use distribute list, so which is not what we want. We want it to point it to its own intra-fabric leaf 1 to reach there, right? So this is what is happening. And when you look at the .8 and 9, that is correctly fine because it is learning through EVPN. Okay. In another scenario, if I do not apply distribute list and the OSPF distance is 12, right? Now I've applied 12 distance, but I still do not apply distribute list. What will be happening? You will see that the .6 is still pointing to WAN router instead of the other leaf. But this time you will also see that the interfabric hosts, that is H3 and H4, are also pointing to its own router rather than going through eBGP, right? With the distance value 2. So distribute list would help achieve or correct this. If not, you will find these outputs, irregular outputs, right? Okay, that's about the best practices. Let's get into the troubleshooting portion. Now, there's a flow which I've tried to highlight. We can ensure that there are no duplicate IP addresses across the VTEPs, meaning the VTEPs, the individual VTEPs I'm talking about, leaf 1, border leaf 1, border leaf 2, border leaf 2, right? Individual leaf VTEP should have their own IP addresses. The VSX environment, when you have that entire VSX is called as one VTEP, and you will still have same IP to that, right? So that is fine. I'm talking about individual VTEPs of the fabric, and one VSX is called as one VTEP. So VSX will have same IP to primary and secondary, including the active gateway, right? So the SVI will be same, the active gateway will be same. That is fine, but I'm talking about the inter leaf communication where leaf 1 and leaf 2 having same IP. It should not happen. You can also check the configuration of the redistribute host route with these commands. Ensure that it's there in those contexts. Sometimes we may get confused with the eVPN context where we are redistributing, which is already there, right? Ensure the command in the context of is present on the border VTEP. That is where it matters, right? The redistribute host route should be on the border VTEP. Similarly, for the BGP, it should be on the border VTEP under context. To check whether that particular host is present in the RIB, you can use this particular command and understand whether it's been successfully redistributed locally, right? And you can use these commands to do that. Ensure the host routes are seen in the RIB and routing table of the peer device, the WAN router, right? And it will be seen as OSPF external route there. And you can use the IP routing table output for that. Ensure the redistribute host routes are externally learned in the routing table, and that peer device would be ideally in a non-VXLAN network, right? You can also check through this command to see whether IPv4 host entries are present on the border VTEP, right? Basically, we are using ARP table, right, and collect that particular host from ARP, send it to the RIB as -32. So you can also check whether, first of all, it's there in the ARP table. Similarly, for the IPv6, you can check the IPv6 summary, neighbor summary for that. With respect to border VTEP troubleshooting, on the border VTEP, you can check IP RIP. As you see, I've marked how it looks like. The new host entry, which is directly connected to that border VTEP, would have an origin type of H. And you see that here. And H is here, host routes, meaning that is locally connected. And you can also see the summary of it and count the number of hosts connected, right? Host routes 3. On continuing on the border VTEP, you can also utilize ARP table, wherein you will see how this .17, which is the directly connected host of border VTEP, is learning. I have lag 50 connected to a layer 2 switch to this VSX system, so I see that learn through that. Rest all host, that is, this one is H3.6 is H1, and then H4 are all learn through VXLAN tunnel, right, with their own IP. On the border VTEP, you find under routing table no connected hosts because you will not see them in the routing table. You will see them under RIP table. Yeah. So .6 you will see learn through iBGP here through leaf 1, and .8 you see it is eBGP, and .9 is through eBGP. That is show eVPN is for your reference on how we are connecting with the VXLAN and the eVPN connectivity and what peer devices are. You can use these command outputs. Now these are those hosts which are being learned and their individual flags through the tunnel. Continuing on the border VTEP, you can also do show BGP VRF unicast and that particular host, the individual host, which is connected to, this is H1, right? So you will find the local preference is 100 for it, right? Now remember the metric manipulation I was trying to talk about. This is a local host, so the local preference is still 100, yeah. And you will see that 20.1.1.8, which is the host 3 on the other side connecting to the border 2. Now it has a local preference of 90, which is what I have assigned with the route map from other fabrics, set the local preference as 90. Yeah, you can check that whether it is assigned with those commands. And also through BGPL to VPN commands, here you will find those local preference values in the solution for individual hosts. On the WAN router, you probably would want to do only two things. One is the RIB table and the routing table itself. On the RIB table, you will see the .6 is H1, .7 is H2, which is border VTEP 1 host, and 8, 9, H3, and H4. They're all getting learned through their own border VTEPs. I'll talk about this IP addressing schema in my feature demo, but trying to highlight that how the RIP table would look like in the WAN router, how the FIP table would look like in the WAN router. This is how it is. You see .6, which is H1, is getting kind of learned through BSX 2 links. Yeah, these are those 2 links. .7, which is the directly connected. This is what we are doing host redistribution on border VTEP, and this is also learning through primary and secondary. Yeah, and you have 8 and 9, which is H3 and H4. It's connecting through or discovering through the router WAN router 2, and there are next hop IPs so and so. Furthermore, outputs which you can utilize, right? I'm just trying to give you what commands can be used to troubleshoot and how to read them with the green marks I've done here. Point noted to be on the metric side, you see this is 25. With that also you can understand that this particular host, whatever that may be, is actually the host which is being redistributed with this feature on the border VTEP, and their metric would actually will be 25. Yeah. Whatever host you learn from EVPN, their metric is something else. It's 100 here. So another tip for your troubleshooting. Further down, WAN router 1, when links to VSX Fabric 1 are intact and not down, right? So when the links between the Fabric 1 border VTEP VSX system and its own router is intact and there is nothing to worry about, the WAN on the router, you would find that everything is seamless. When there is when the router 1 are intact and not down, WAN router 2, when links to VSX Fabric on WAN router 1 are intact and also not down, right? So when that happens, you will see that the individual host of a particular site is getting redirected to the other WAN router, go to the other site border, and come back to EBGP. So what I'm trying to show is how a failover is achieved, and what you can see if there is a discrepancy in the next hop, you will understand that there is a link failure in your existing router. So these are those commands which I'm trying to highlight. Okay. And this one would be when the VSX secondary is down, the primary would still be there, right? So this 101.1.1 is still the primary next hop, and earlier you would seeing 2 routes here, right? Now the secondary has gone down, so you will only see the primary and still there. So there is no issues. There is a failover within the links. If the VSX Fabric 1 border VTEP to its own router itself has gone down, that is both the links goes down, it goes to the router 2, and that is what you see here. With respect to demo, I would want to highlight what the setup looks like. I've expanded or maximized the setup so that you can read through the nomenclatures of this particular setup and how it looks like, what is connected where, right? I just want to take 1 minute to ensure what's most important and what you have to remember. We have this site 1, Fabric 1. We have DC2, Site 2, Fabric 2. They're connecting through interfabric, yes. VRF1 is in our setup. We are concentrating on VRF1. VLAN 1001 is the one which is getting stretched. All these hosts 20.1.1.6, 7, 8, 9 are all on 1001 with their SVI as 20.1.1.1. These are, I have only one spine connecting to leaf 1. I have only one VSX system. on fabric 1. I have non-VSX system acting as border VTEP2 on fabric 2, right? And spine, a single spine on the fabric 2 as well. So this is my setup, exact setup. And the loopbacks you see here are all highlighted. And for the VXLAN tunneling and for the peering, it's all here for your reference. Okay. 1.1.1 is for border VTEP1. This is border VTEP. As you see, border. The host name would be like this: fabric 1, leaf 2, VSX primary, and border VTEP. Similarly, fabric 1, leaf 2, VSX secondary, border. Similarly, fabric 1, leaf 1. This is the leaf 1 and the spine. On the other side, fabric 2, we have fabric 2, leaf 2, and the border VTEP. This is the border. I have highlighted the host name as border for easier understanding. And then you have fabric 2, leaf 1, non-border, which is the other side of the leaf. So they are all IBGP connected within each other and eBGP connected between the fabrics. Now, coming the interesting part, I'm using the OSPF, right? So you can use BGP also. Now on the upstream from border VTEP, I have two links from fabric 1 going to a router here. I have my own router sending OSPF default route to the border VTEP as we discussed. This router has a static route pointing to one of my VMs, which has an IP 21.21.21.22, right? Just remember this IP, that's a VM. Consider this as the internet. And I have router 2 here, which is the WAN router for the fabric 2 and its own border VTEP 2. Okay. All right. These are the most important thing, and other stuff I've already highlighted on how we are doing the lower metric, the route maps, the distribute list, the distance. All of that is already in place. The next slide is I have tried to remove the extra lines just to highlight the subnets between the links, right, which I have here, so that you understand what from the outputs that we have 101.1.1.network from primary to router 1, from secondary to router 1 we have an ROP of 102. Similarly, on the other side, border VTEP 2, you have 103 going to its own router. Router 1 and router 2, which is non-VXLAN, they are connecting on a subnet 51.1.1.0 network to each other. This is an ROP here. Yep. So these are the most important subnets which you would be looking at in my demo. Okay. All right. Since I'm assuming you have picturized the topology, let me try and play the demo which I have set up. Okay. So what I'm trying to show here is the individual devices. This is the border VTEP. Spine 1, fabric 1. Yes. Leaf 1, non-border VTEP, fabric 1. Then I have leaf 2, VSX primary, border VTEP. This is our VSX border of fabric 1. This is VSX border fabric 2. Then I have layer 2 switch connecting. Then I have fabric 2 spine 1, right, from the other side, fabric 2. Then I have border fabric 2 of leaf 2 from the fabric 2. I have the non-border fabric 2. Then I have the WAN router, which is connecting to site 1, fabric 1. I have router 2 connecting to site 2. These are all the host names of the devices. Now let's try to see what we are trying to achieve. Now, I would be trying to show you what the configuration of OSPF VRF1 is there. Sorry, this is not the VRF, just the show run OSPF. You will see I have OSPF running and I do not have redistribute host route command. So I'm trying to show you how it works without this feature. So redistribute host route is not there. Now let's see what the ARP table looks like, and you will see that I have .6 host 1 learning through IBGP, .8 learning from eBGP, .7 which is its own directly connected through layer 2 switch, and .9 from eBGP from the other fabric. So I have all the hosts right in the ARP table. From the router, my own router, right, I will try to see how it looks like in its routing table. You will see that there is a /24 network. Yes, that's fine, but we also have .7. Okay, so those two are the VSX IP addresses. .7, which is the connected host, it's pointing towards the router 2, WAN router 2, instead of the VSX border VTEP, right? This is the problem we were talking about. Now, without this, you will be seeing that the routes are running in the internet instead of directly coming to its border VTEP. 51 network, you see. Okay. So on the router 2 also, you would see the same, and its own connected border host is .8, and it's pointing to router 1, 51.1.1.1 network. So basically, you see the problem here, it's not pointing to the border VTEPs of its own. Instead, it's talking among themselves in the non-VXLAN network. Okay, so let's get into the router OSPF context. Use this feature, redistribute host route. Okay, redistribute host route looks like this, and hit enter. We'll do the same on the secondary border VTEP. So we have a VSX system, right? So we have to do that over there as well. And I do the same on the Fabric 2 border VTEP. Okay. So now we have done all that. Now let's see on the router, the WAN router of Fabric 1, how it looks like. Now you see .7, which is the border VTEP host. Host 2 is pointing to VSX primary and secondary /32. It's not pointing to WAN router 2 like earlier. For 8 and 9, it is pointing to WAN router 2 because that is how it's supposed to go. Similarly, on router 2, you will see .7 is pointing to router 1 instead of its own border VTEP. It's supposed to go through the router 1 and then go to border VTEP 1 to reach border VTEP 1's host. So now let's see how, with this setup, with the intact solution, the reachability is. So this is my VM host 21.21.21.22, which is on the internet, as I said, right? So let me do IP config to show you my IP. This is what that is. The router 1 is pointing the default route to this, right? So I'm trying to reach all the hosts from internet is what I'm trying to show here. So I'm trying to reach host 1 of Fabric 1, successful. I have host 2, which is on the border VTEP 1 of Fabric 1, successful. Host 3, which is on Fabric 2 border VTEP, and host 4, which is on the leaf of border Fabric 2. So all are successful, right? Now let's try to find what do you say, a failover scenario. I have 149 and 150, which is connecting to our these two are the interfaces on our router 1 connecting to the VSX border VTEP, right? And their IP addresses have already shown. So let me try to show you here. I'm talking about this interface. I'm going to shut down this interface or one interface, show you how secondary route link is being utilized to reach the host failover. Then I'm going to shut down both the interfaces. That means this scenario is down. For border VTEP, this uplink to the router 1 is gone down. So basically from VM, it will go via this path, go to the other WAN router, go to the other border VTEP, go through EVPN and reach the host of Fabric 1. That is what we discussed in the data path use case and control path, right? So I'm trying to show you the failover scenario. So 149 and 50 on router 1, WAN router. Here we go. So 49, this is the primary switch, primary VSX switch. I'm going to shut that down. Okay. And you will see on from the VM, from the internet, or you will see the routing table itself. You have one route now through secondary. Yeah, we can try to check the pings as well to .6 and 7. it's successful. There is no ping drops. There is no reachability issues. Now, let's also try to shut down the secondary. Both the links have gone down, so there is no WAN router for Fabric 1. Now you see it is going through WAN router 2. Let me show you that. You see, I shut this down. It's going through this on WAN router 2, 51.1.10 network. Yeah. And you still have reachability for both the network. I'm just going to pull them up. And you see, it's just going to take a little time to have both the routes 100, 101 and 102. Okay. Yeah, it's come up. Okay. So that's about the feature demo.
With that, we are at the end of the session. Thank you everyone for joining.